Hey guys, you there?
Hello.
I just got disconnected. Can you guys hear me? Philip?
Hello.
Yeah, I can hear you. Yep. Michelle, can you hear me?
Yep.
Okay. Sorry about that. So this question here last time, you guys were struggling with this one. So let's do this together. So when you have a triangle like this, and let's say this one is 1 and root 3 and 1. So let's say this one is root 3 and this one is 1. Okay. Then how much did I say was that the hypotenuse? This value here. That was 2, right?
Mm.
Yeah, that was 2. Why? Because it's the Pythagoras theorem. What's a 1 square plus root 3 square? This is equal to 2 square, isn't it? Because that's a 4. 4 equals to 4. Now, and I said this angle here is how much? We know that sine of 30 is equal to? So basically, you guys have to memorize a few things, few values for trigonometry, and it's going to be quite helpful. Just give me a second. My tablet. It's not working. Oh, it's not working. Yep. Okay. Yeah. Okay. So sine of 30, you guys have to memorize this one. So sine, cosine, and tan. And with the angle of 0, 30, 45, 60, and 90. And it'll definitely help you if you just memorize this one. Sine of 0 is 0. Sine of 30 degree is 1/2. And root 2 on 2, root 3 on 2, and 1. Now this one here is the other way around. 1, root 3 on 2, root 2 on 2, 1 on 2, and 0. And this one here is 0, 1 on root 3, 1, root 3, and this is undefined. So if you just memorize this, your mathematics will be a lot easier when you go into year 11 and year 12. Some students just invest like 5 minutes or 10 minutes in this little table, and they just memorize it, and they just keep using and using and using, and they save like lots and lots of time. Okay, some people just don't bother memorizing it, and they just end up wasting a lot of time. So the choice is up to you, because every time something like this show up, and if you don't have this table ready in your mind, your understanding level will just remain at around 30%, like 20%. Okay. But when I explain these things with the angle, then when you have this table ready in your mind, then you'll definitely understand like 90% or 95%, 100%. Okay. So, what is this angle? Well, the answer is 30 degree, because we know that sine of 30. We know that sine of 30 is equal to 1/2. So what's sine of this one here? Definitely that's a 1 on 2, isn't it? 1 on 2. That's the opposite over hypotenuse. So this is equal to 1/2. What is this? What is the so if that's 30 and this is 90 here, well, how much is this angle over here? That's a 60 degree there. So what is for example, cosine of 60 degree? If this is 60 degree, then the cosine would be adjacent. This will be the adjacent, if that's the angle that you're talking about. Adjacent over hypotenuse, right? So you can see that cosine of 60 is also 1/2. So they're all related. This triangle basically confirmed. This triangle, if you memorize this triangle, so if you don't want to memorize this triangle. √3, 1, 2. And this is 30. And this is 60. If you memorize this, then you'll be able to figure out what sine of, let's say, 30 is. What's the sine of 60? What's the sine of 30 without memorizing this one here? If you just memorize this picture, that's a 60 there. So sine of 30 is opposite over hypotenuse, which is 1/2. What's the sine of 60? This is 60 here, so opposite is this one over hypotenuse. So that's √3/2. Is that right? So that's all in here as well. So that's how you do it. All right, let's have a look at this one. This one is giving you this triangle, and that point right there is negative √3, 1. That means this length over here is √3, and this length over here is 1. Is that right? So if we memorize the triangle, that's 1 √3, negative √3, because it's going in the negative x direction. And how much is this angle, Michelle?
30.
Mm-hmm. So the question was, how much is this angle, true?
Yes.
That must be 150, that's it. 150. So we know that 30 degree is pi over 6, so therefore 150 is equal to 5 times this one, right? So therefore 5 times by pi and 6 is 5 pi and 6. Like that. Okay, so that's the end of that question. Now let's move on to this worksheet. So we are now up to, so we were doing metallic bonding last time. Was that the last topic that we did? So look. Yeah, so I asked you guys to watch this video, right? Okay, so we did this one last time. We also did this one too. And the answer for this one was, we didn't do this one, sorry. Okay. So we're going to talk about boiling points and melting point today. And we can do a lot of questions today as well. So I'm not sure if I explained this one last time, but I explained, maybe I did. Did I talk about intermolecular forces before?
No.
No. Okay. Let's talk about that today. So last time we talked about 3 kinds of bonding. So first one was the covalent bonding, but that's a non-polar covalent bond. And that happens when you have the electronegativity table. This is the periodic table, and you saw some numbers, right? And fluorine has the greatest intermolecular force. Let's have a look at that. I mean the electronegativity, sorry. So I think I gave you this table. This one here. And also I showed you electronegativity and bond. This one here. Do you guys remember this one from last time?
Yep.
Yeah, so let's go over this again. So nonpolar covalent bond. So polar bonds, covalent bonds is when you share stuff. This is sharing, covalent bond. Ionic bond is completely donating electron from one atom to another. That was ionic bonding. And I said the covalent bond occur between nonmetals. So up to here, this happens between nonmetals. And ionic bonding happens between what? Between nonmetal and metal. So the reason for that is because if you have this periodic table, if you divide this into two parts, this side is what? Is this metal or non-metal, Michelle?
Metal.
That's non-metal here.
Oh.
And the other side here, that's metal. So if you, for example, take this one here, fluorine, and calcium, for example, they are too far away, right? So the electronegativity difference is, in this case, 2.7. So 2.7 is somewhere there, and that's classified as ionic bonding. Michelle, does that make sense?
Yes.
Mm-hmm. And Philip, if I take carbon and hydrogen, by the way, hydrogen must be actually here. It's actually classified as non-metal, even though it's right there. Philip, what's the electronegativity difference there? That's 2.5 and 2.1, so it must be, the difference is 0.4.
4.
So 0.4 is right there, and that's classified as pure nonpolar covalent bonding. Okay, so there are three kinds of bonding here. Hello, Chris.
Hello.
I'm just wondering, is my voice loud enough?
Yeah, it's loud.
Okay, it's not that quiet, is it? So we have number one, we have covalent bonding. So this one is non-polar. The polar is when one side is positive and the other side is bit negative. And this happens between non-metals. Non-polar covalent bonding, like this one here. So these are type of bonding between two. When you have polar covalent bonding, and this one is between also non-metals. And number three, you can write this down. You have ionic bonding. And this happens between non-metals and metals. Okay. So that's all clear. Now, we're going to talk about H2O. So H2O is oxygen with 1, 2, 3, 4, 5, and 6 electrons around it. And we saw this one last time. Hydrogen has 1 electron, and hydrogen has 1 electron, and they share. So hydrogen is quite happy here with 2 electrons. And oxygen is also quite happy with 8 electrons. I'm going to ask you this one. What kind of bonding? So this is known as, this one is oxygen here. And then it has a bond like this, a bond, and then hydrogen and hydrogen. And this must be bent. We talked about this last time through what's known as VSEPR. And we have 2 lone pairs. That's a lone pair here. Remember this? Lone pair here. So you have lone pair here and lone pair here. Makes sense. And because of the lone pairs, it bends the structure. Makes sense? Now I'm going to ask you this one here. What kind of bonding is this between oxygen and hydrogen? Is it the nonpolar covalent bond, or polar covalent bond, or ionic bonding? You have to look at this table, and you have to look at this table here as well. Chris, do you have any idea what type of bonding this is? Michelle, would you know?
Yeah, it's covalent bonding.
It's a covalent bonding, right? Why?
Because there's two non-metal.
The two non-metals. What's the difference between those two? Hydrogen and oxygen. 3.5 minus 2.1?
Yeah.
1.4, right?
Yeah.
1.4. So let's use a calculator. In case we need it, I'm just going to put it here. So 1.4 is somewhere here, isn't it? Somewhere here. Does that mean it's a polar covalent bond, like this one here, or non-polar covalent bond? Anyone? So Michelle just told me that this one here is a covalent bond. But is it going to be a non-polar covalent bond like this one, where there is no charge, or is it going to be a polar? Because we are right here.
It's polar.
It's polar. That's right. Not too bad, right? Polar. That means when you look at this whole thing, the electron is more toward here. So when you have this bond, you see how this bond here is made up of these two electrons here. But these two electrons are closer to the oxygen. Why? Because oxygen is more electronegative. That's 3.5 versus hydrogen, which is 2.1. So this one pulls the electron to itself more than hydrogen. So it's going to be polar, but what's going to happen is that this oxygen here, so when you look at this whole thing, this side is more negative, so we use the symbol delta negative, and this side is delta positive. Does that make sense? So that's a polar covalent bond. And same with this one here as well. So this is going to be delta negative here also, and delta positive here. So delta here, this symbol here means lightly. Now, what's going to happen though, is that these two are going to create, so it's going to cause this whole molecule to be like that, and then this side is going to be a little bit positive, negative, and you see how these two ends are positive, right? So this side here, down here, is going to be slightly positive. Okay, so this is the water molecule. So the water molecule is going to look kind of like this. Now write this down. If a molecule has one side positive, the other side negative, we call it a dipole. So what does it mean by dipole? Di means two. You have two poles. You know, North Pole and South Pole? This is positive pole and negative pole. So this is a dipole. Okay, this guy here is a dipole. Of course, you may argue, oh, there's a negative there, positive there, and there's also positive there. And there are 3 poles. You can say that, but this positive here and positive here, this will combine into just 1 pole. Okay, so this can be considered as a dipole. So why is this important? Because we're going to compare that with carbon dioxide. Carbon has 1, 2, 3, 4. 4 oxygen around it. And oxygen has 6 electrons. 1, 2, 3, 4, 5, 6. Oxygen here, 1, 2, 3, 4, 5, 6. So the way this one bonds was, we drew this one last time. There's a double bond, O. So it's like that. So this was the Lewis structure. So we call this one as Lewis dot structure. So whenever you are doing dots, representing electrons as dots, we are doing Lewis dot structure. So it definitely takes some time for you to develop these skills, but notice some difference here. So you see how this oxygen has 2 lone pairs, and what did they do, Michelle? When you have lone pairs, what did they do? Chris? Philip? Can anyone tell me what lone pairs do? You guys can enable your microphone. Yeah. When we did this one here, we did this question last time. Remember this question, guys?
Lone pair push electron.
Yeah, lone pairs, they repel each other, right? So lone pair can push another lone pair. Lone pair can push a bond here, right? What was the answer to this question here, guys? Was the lone pair repulsion the strongest, or lone pair bond pair strongest, or between bond pair and bond pair? Which one was the strongest? It was just about a week ago, wasn't it? And I think you guys understood this pretty well, this question. Chris, do you remember what the answer was? So the answer was A. So that's what we did last time. I'm just lowering my desk, guys. Okay. By the way, there will be another lesson at 8:15. If you guys want to join it, you're more than welcome to. So this is with many other students doing chemistry, but you may find this class quite difficult because it's with higher level students, but you're more than welcome to join it for free if you want. Otherwise, it's completely okay. So let me know if you want to join, okay? So, but I really have to achieve this tonight. There's one thing that I really want to achieve tonight, which is the intermolecular force. Now here, in this case, there are no lone pairs. So you've got the double bond here, double bond here. So this one here is a linear structure. So this is a linear. And what happens is, this is still a polar covalent bond. So as you can see, carbon and oxygen here. So carbon and oxygen has difference of 1. So that means it's around here. So it's also polar covalent bond. Now, so the difference between water and carbon dioxide is So this is hydrogen there, hydrogen there. This side is slightly negative, and this side is slightly positive, and this is slightly positive. This one here, oxygen is slightly negative, and the carbon is slightly positive. So when you see this bond here, this side is slightly negative, this is slightly positive. When you see these two, this is slightly positive, this is slightly negative. But the thing is, you see, when you have this sort of structure, have a look. I'm going to draw an arrow, and the arrow is going to be always from plus charge to minus charge. Okay, so I'm going to use this convention. Now have a look at this structure here. This is carbon dioxide. This one is from positive to negative. So I'm going to draw an arrow this way. I'm going to draw an arrow this way. So carbon to oxygen, positive to negative, and positive to negative. So what do these arrows do, guys? They can cancel each other, is that right? They can cancel. So what happens is, and what about for water? Water is plus to minus, so it's going to be this way and this way. So do they completely cancel each other out? The answer is no. When you add these two, you're going to get this one. When these two cancel, when someone is being pulled this way and pulled that way, you just get zero, nothing. All right. But when something is pushed that way and pushed that way, it's going to be pushed upward, right? Guys, are you guys still there?
Oh, yeah.
Yeah.
Yeah. It says my internet is a bit unstable. Can you guys hear me pretty well? Hello? Can you guys hear me well?
Yeah.
All right. Cool. Maybe sometimes I'm not hearing you guys, even though you guys answer. Do you think that happens?
Sometimes.
Okay. All right, just do let me know if I'm breaking or if things are slowing down, okay? So in this case, what you end up is, this one has polar bonds are there. So this one has polar bonds are present. This is a polar bond, this is a polar bond. As you can see, there's a plus and minus. But this one ends up being a non-polar molecule. Why? Because it cancels out. This one here this one do have polar bonds. And because it is bent, and why is it bent? Because of the lone pair. This one is not bent because there is no lone pair. So this one is polar. This is still a polar molecule. So what it means is this. This one has polar bonds, but the overall, it's not polar because they cancel. This water molecule here has polar bonds, and they don't completely cancel out. So you get a polar molecule. So let me show you what these tiny little difference here, non-polar molecule and polar molecule, what this one leads to in real world, okay? So they are about similar sized molecules. Now, water molecule is like this. Water molecule looks like that. And one side is negative, the other side is positive. So if there is another water molecule like this, have a look, what's going to happen between these two? Anyone? Michelle, what's going to happen between these two if it's plus and minus?
Pull each other.
Pull each other, attract each other, right? That's right. So if I have another water molecule here, and this is a negative side, and this is a positive, so it's going to attract each other, true?
Yes.
So this is a bond, that's a bond, and that's a bond inside there. So this is an oxygen, this is hydrogen and hydrogen. Oxygen and hydrogen, like this. Now we call this one the interaction between molecules. So this one is known as the intermolecular force. And this is an attraction. Okay, this is an intermolecular force, and that's an attraction there. I want you to maybe think about maybe another system. So carbon dioxide is linear, right? Carbon dioxide is linear. So oxygen, carbon here, oxygen here. But because this one canceled out, there is no positive or negative anymore. It started with positive and negative and positive and negative. So the bond itself is polar, but it's all canceled out. So I'm going to show you. I'm going to draw another carbon here. Another carbon here, dioxide. Now, would they attract each other well as this one here? The attraction here is weaker, isn't it? It's a lot weaker because there is no positive, there is no negative. This is all, you know, nothing really there. So if we actually Google, the boiling point, for example, boiling point of water is 100. So we know that water boils at 100 degrees Celsius. So that means you have to heat it up to this one so you can break this bond. If you break this bond completely, then they become vapor, they become gas, right? Now, how easy is it to break this bond over there? If we look at the boiling point of the carbon dioxide, this happens around negative, like something like this, negative 78 degrees Celsius. So minus 78 degrees Celsius, then this is already gas. So here's the thing, why water stays as liquid in 20 degrees Celsius, for example? Why does water stay as liquid? The reason is because of this intermolecular force between water molecules. They strongly attract each other. That's why water stays as water. So if it wasn't this particular property of water, then water wouldn't stay as liquid. It will stay as gas in 20 degrees Celsius. Does it all make sense to you?
Yeah.
Now I'm going to summarize this. So there are 3 types of intermolecular force. First one is weak dispersion force. And weak dispersion force is the only force between nonpolar and nonpolar. So this is a nonpolar, this is nonpolar, right? Maybe this is between non-dipole and non-dipole. But I'm going to explain later that weak dispersion force is not only present here, but it's also present in here. So what is the name of this force here? I said this is the weaker force because there's no positive sign or negative sign. So this force is known as the weak dispersion force right there. This is the weak dispersion force. And this is between a non-dipole, a non-dipole. These are not dipoles. Second force is known as, so you see how we talked about 3 different bonds, this one here, this one here, this one here. So these are often called intramolecular force. intramolecular force. That's inside of the molecule, like in here. But what about this one? This is known as intermolecular force. This is between molecules. Does that make sense? Between molecules. So there are 3 different types of intermolecular force. So the first one is weak dispersion force. Second one is the dipole. It's just called dipole-dipole interaction. So this one is between a dipole, which is one side is plus, one side is negative, and another dipole. You have another dipole, this is plus and minus, and there's going to be some attraction between those two, right? So this is known as dipole-dipole interaction. So these two, and then the third one is known as hydrogen bond. By the way, you see this water here? That's a dipole. This is a dipole. So the interaction between these two is known as which one? Weak dispersion force or dipole-dipole?
Dipole-dipole.
Dipole-dipole, that's right. However, it is actually known as hydrogen bond, this one here. So hydrogen bond is a type of, so hydrogen bond is actually a dipole-dipole. I'm going to introduce hydrogen bond, but it's actually, it's just a stronger version of the dipole-dipole. Dipole-dipole. Okay, so what is it? It's between hydrogen, which is a slightly positive, and oxygen, which is slightly negative. So you see here, this is oxygen here, right? And it's attracted to hydrogen there, true? So if you have hydrogen attracted to oxygen, or hydrogen attracted to nitrogen, or hydrogen attracted to fluorine, and that's all slightly positive and slightly negative and slightly positive and slightly negative, and these are known as hydrogen bond. So now let's move on to some questions. Let's do some questions now. So we can do a lot more questions. Okay, let's have a look at this one here. This one says, why is the boiling point? So I'm going to write this one here first. The greater the intermolecular force, the higher the melting point and boiling point. So melting point is going from gas, solid to liquid, or liquid to solid, you know. Boiling point is where you go from liquid to gas, or gas to liquid. For example, water, melting point is 0 degrees Celsius because water becomes ice at 0 degrees Celsius. It melts at 0 degrees Celsius. Boiling point is 100 degrees Celsius for water because water boils at 100 degrees Celsius, and it becomes, so a vapor can become liquid water at 100 degrees Celsius. Okay. But if the intermolecular force, so if you have the intermolecular force, so this one here and this one here. So if the intermolecular force between molecules is strong, then it'll be difficult to separate these two. That's why it'll be that's why it'll have high melting point and high boiling point. All right, that's what it's saying. This is saying. Have a look at NH3 compared to PH3. So P, H, H, and then H, and it has this kind of look. And nitrogen also has a very similar look. And this side is going to be slightly negative, and this side is going to be slightly positive. Same with this one, negative and positive. So if you have another thing, I'm just going to take this one and then copy. Oops. Hold on, I cannot copy this one. Maybe I'll do it this way. If I have another one like that, there will be some intermolecular force between these two and between these two, right? So if these two are in a separate container. So it's saying that why is the boiling point of this one lower than the boiling point of this one? That means this is weaker. The interaction between this is weaker. Doesn't mean there's a weak dispersion force. This one is a bit stronger. So why is that the case? It says that pH3 is non-polar, whereas NH3 is polar. Is that true? Is this non-polar? Chris, is this non-polar? Are you still there? Maybe your microphone is still not working. Okay. Is this polar, Chris? This is polar, right? But why? Because it's a negative and this is positive. So definitely this is wrong because pH3 is definitely polar. This is wrong. NH3 is polar, so we know that that's right. So that's negative, positive. So when you have positive and negative, that's polar. Another term for that is dipole, right? So B, and pH3 is not hydrogen bonded, whereas NH3 is hydrogen bonded. This is the correct answer. So if you go back to this one here, so there are three types of intermolecular force, right? This is the weakest kind of force. This is the next dipole-dipole. That's between a dipole, which is polar, of course, and another polar molecule here. But hydrogen bond is something that is the same thing as dipole-dipole, but it's a bit stronger. So that's positive and negative. So whenever you're dealing with a hydrogen oxygen or not hydrogen nitrogen or hydrogen fluorine, these are a bit stronger than the dipole-dipole. So let's go back to this one. So Michelle, what kind of interaction is happening between this one and this one? Is it the weak dispersion force, or is it dipole-dipole, or is it hydrogen bond?
Dipole-dipole?
This is hydrogen there.
Oh, then
hydrogen there.
hydrogen bond.
So between hydrogen and nitrogen was the hydrogen bond. That's right. Philip, what kind of interaction is happening here?
Dipole.
That's right, dipole-dipole. Dipole-dipole is between any like plus, minus. If you have plus and minus, then you have dipole-dipole, right? So this is not weak dispersion force, but this is a dipole-dipole, right? And definitely this is stronger than this one. So that is the reason why, yeah, this is the reason. pH3 is not hydrogen bonded, whereas NH3 is hydrogen bonded. Now, number one is also known as van der Waals force. Yeah, we can talk. So weak dispersion force, another name for that is van der Waals force. Van der Waals force. All right. I just need to tell you that we know that between nonpolar and nonpolar, so that's not positive, negative, not positive, negative, what kind of force exists between these two? Chris? It's the weak dispersion force, that's right. So is there any dipole-dipole here or hydrogen bond? The answer is no, that's right. Oh, actually, I was reading your comment above, sorry. So the answer is no. What about this one, plus and minus? Plus and minus. Philip? Dipole-dipole, that's right. Let me ask you this, Philip. Would there be, so there's a weak dispersion force here. So there's only number 1 here, right? And this one is number 2, true?
Okay.
But is there weak dispersion force in here?
No.
So a lot of people think, like Philip, that there is no weak dispersion force. But you should know, I just haven't taught you this yet, the weak dispersion force is everywhere. In here as well, in here as well. And if you have like a dipole and like a non-dipole, then of course this would be, of course this wouldn't be the dipole-dipole, right? This is not dipole, this is non-dipole. You're saying weak dispersion force overpowered by other, yeah, that's right. In this case, so in this case over here, the dipole-dipole interaction is like way stronger than the weak dispersion force. So that's right, you're right. The weak dispersion force is simply overpowered by other types of forces. But just need to know that the van der Waals force or weak dispersion force are everywhere in every interaction. Sometimes the weak dispersion force overpower these two. In this moment right here, these two are overpowering this one. So the weak dispersion force can overpower other intermolecular forces if the size of the molecule get larger. So if you have like a long stuff, like if you have like a long molecule, then the weak dispersion force can actually overpower. So that's what's going to happen. Now have a look at C. It says van der Waals forces are weaker in pH3 than NH3. That may be the case. That may not be the case. But I would say that the weak dispersion force, let's have a look. Which one is a heavier molecule? Let's have a look at the periodic table over here. So the nitrogen is here, and the phosphorus is here. So definitely this one is a heavier molecule than this one. This is heavier, and this is lighter. Which one is going to have more van der Waals force? No, nitrogen isn't heavier. Nitrogen is actually above the phosphorus. Phosphorus is down here. So as you go down this periodic table, see, you're increasing mass. You're increasing number of protons and neutrons and things like that. So this is definitely heavier than this one. Yeah. So because it's heavier, when you compare the weak dispersion force or the van der Waals force, this one is greater than the weak dispersion force of this guy. So have a look. It says that van der Waals force are weaker in pH 3. Is that right? It's weaker in here. See, so this is wrong. It says molar mass of pH 3 is greater than, oh, that is true. This is a true sentence. but this is not the reason why. So you see, when there is no dipole-dipole interaction, when there is no this, when there's no that, if these are not polar, then a heavier molecule will have a greater intermolecular force and therefore greater boiling point. So when you have a greater molar mass, then greater intermolecular force, right? If greater intermolecular force, then greater boiling point, right? But so this is a true statement, but this cannot be the reason. This does not explain why this has lower boiling point than this one. So have a look. I'm going to summarize this one right here. So pH3 has more mass. NH3 lower mass. So if we're just talking about the weak dispersion force, this is going to have higher weak dispersion force. This is going to have lower weak dispersion force. If this one has higher weak dispersion force, then this will lead to higher boiling point, and this is going to have lower boiling point. But why doesn't that happen? Why this one is true and true, but this one is not true? The reason is because there is another force. This one has dipole-dipole, and this one has hydrogen bond. So this guy is the winner. So even though this guy is winner, yeah, this one overpowers. So that's why this is not true. Okay. All right, we'll call it a day, and I'll see you guys in the next lesson. If you want to attend it, you're more than welcome to, all right? I'll send you the link, all right? Bye, guys. I'll send you some homework as well.